This week in Physics 231C, the topic is Chapter 4, Forces and Newton's Laws. Now, at the end of this week, there'll be an exam which will cover Chapters 2, 3, and 4. So let's start with a quick review. Chapter 1 was just a chapter on measurement and units, powers of 10, on math. That's not explicitly on the exam. The chapters 2 and 3 were chapters on kinematics, the mathematical description of motion. And those chapters will be on the exam. Hopefully you've been taking notes and writing down the important equations, because you need to make an equation sheet, one sheet of paper with equations on it that you can use while you're taking the exam. Here are some basic equations from on kinematics, let's say. Position is a vector in 2 dimensions. So we could write it as x vector of t, or we could write it in terms of Cartesian coordinates, x of t and y of t. That's position. Velocity is another vector. Velocity is the rate of change of position. It's the change in x divided by the change in t. That's the average velocity over a time interval delta t. But if delta t is very small, then this ratio is the instantaneous velocity at the time t. Or in terms of Cartesian coordinates, it's delta x over delta t in the x direction and delta y over delta t in the y direction. And then finally, acceleration is a third vector. It's the rate of change of velocity, delta v over delta t. Now, in Chapter 3, we applied these methods of kinematics to various kinds of problems. Free fall in Earth's gravity, projectiles, an object moving in Earth's gravity both horizontally and vertically, circular motion, where there is a centripetal acceleration. If an object's moving on a circle, its velocity vector is directed tangent to the circle, and its acceleration vector, if the speed is constant, is directed towards the center of the circle. If the speed is increasing, then there's also a component of acceleration tangent to the circle. Well, that's the review. Now the preview, Chapter 4. Chapter 4 is called Dynamics. Kinematics is the mathematical description of motion. Dynamics is the science of forces. In dynamics, we're asking, how do forces affect motion? And the most important equation is Newton's second law. Force is mass times acceleration. So we have to introduce a new quantity, mass. Acceleration we already know from kinematics, but we have to introduce a new quantity, mass. And then also force. Force is a push or a pull. We'll say more about that. And according to Newton's second law, this is the relation between force and acceleration. They're proportional. They're in the same direction as far as vectors are concerned. And there is a proportionality constant, which is nothing but the mass. So now here is the chapter. It has 5 sections. Force and mass, Newton's laws of motion, some examples of Newton's laws, A specific case of of force is friction or drag. Friction with the atmosphere is often called drag, the drag force. And then there's a separate section on uniform circular motion. We studied the kinematics of uniform circular motion. How does dynamics produce uniform circular motion? So we start with force and mass. First of all, these words have meanings in everyday life, but in physics they have to have more technical meanings. So what is a force? Well, we could look it up in the Oxford Dictionary of Physics, and here's what it says. Force, the definition of force. The agency that tends to change the momentum of a massive body, defined as the rate of increase of momentum. What's momentum? Well, for a body with mass m traveling with velocity v, the momentum is m times v. So the rate of change of momentum is the mass times the rate of change of the velocity. Rate of change of velocity, we know from kinematics, is the acceleration. So you see here in the definition, we already have the equation, F equals m times a. Continuing on reading the Oxford Dictionary of Physics, the SI unit of force is the Newton. Who's that named after? The abbreviation is capital N. Then there's one more statement in the Oxford Dictionary of Physics. Forces always occur in equal and opposite action-reaction pairs between bodies, though it is often convenient to think of one body being in a force field. So, apart from field theory, which is really the subject of electricity and magnetism, that doesn't really come along until Physics 232. Every force requires two objects. One object to exert the force, and the other object to experience the force. And for every action, there's an equal but opposite reaction. So again, that's Newton's third law. That's included in the Oxford Dictionary of Physics in their definition of force. So what is a force? In grade school, you probably learned a force is a push or a pull. Well, that's probably a pretty good way to think of it. Something has to be exerting a push, and then the second object is experiencing the force of that push, or a pull. So force is something we experience every day. I mean, every day we experience forces. We make a push on something, or something pushes on us. So we experience the force, or a pull. Okay, so we've seen a good, strong definition of force from the Oxford Dictionary of Physics. Now, what is mass? Well, again, we could look it up in the Oxford Dictionary of Physics. So here's the definition quoted directly from the Oxford Dictionary of mass. What is mass? A measure of a body's inertia, i.e., its resistance to acceleration. Mass defined in this way is called inertial mass of the body. But mass can also be defined in terms of the gravitational force it produces. The mass defined in this way is called the gravitational mass. In the 19th century, this Hungarian physicist Loránd Eötvös showed by experiments that gravitational mass and inertial mass are indistinguishable inertial mass is equal to gravitational mass. That's already kind of implied by Newton's theory of gravity, but Eötvös did the best experiments. Now, the Oxford Dictionary of Physics also makes mention of the relation between mass and energy. Everybody knows E equals mc squared. Everybody knows that equation. It's not quite correct. That's only when the particle is at rest, or when the mass is at rest. More generally, delta m is delta E over c squared, or delta E is delta mc squared. If there's a change in mass, there's a corresponding change of energy. Then the Oxford Dictionary of Physics, at least the copy of it that I have, which is somewhat old, adds one more statement. The origin of mass is not yet fully understood. That was in the Oxford Dictionary of Physics, published probably sometime in the 1980s. That statement's no longer true. Since that copy of the Oxford Dictionary was published, the origin of mass is fully understood today. Physics makes progress. Now, let me make two comments. Newton's theory of gravity involves mass. It's gravitational mass. And in Newton's theory of gravity, the force, the gravitational force, when two masses are interacting, they're both exerting forces on each other. That's called gravity. And the force is G, that's a universal constant, times m1 times m2 divided by r squared, where m1 and m2 are the masses. R is the distance between the two objects. I think of them as two spheres. R is the distance between the centers of the spheres. Now, we'll come back to Newton's theory of gravity later in the semester. That'll be chapter 9. But this chapter, chapter 4, is mainly using mass as a measure of inertia, the resistance to acceleration. Just be aware of the fact that it also plays a crucial role in the theory of gravity. Come back to that. Now, what about this statement that the origin of mass is not fully understood? Well, today it is fully understood. The origin of mass is in the interaction with the Higgs field in the standard model of high-energy physics. Maybe you heard about the discovery of the Higgs boson some years ago. Well, the Higgs boson is related to the Higgs field. The Higgs field and its interactions with elementary particles gives those particles mass. Also, for an object at rest, we have this equation m equals E over c squared. It's usually stated E equals mc squared. Now that goes back to Albert Einstein. The question is, what is this energy? Well, in our current understanding of fundamental interactions, that's the energy of the fields that produce the particle whose mass is m. So this is a known energy. So that's why I say the origin of mass is not yet fully understood. Yeah, well, since that dictionary was written, we now know the field energies that are present in elementary particles. All matter is atomic. The atoms are made of elementary particles like electrons and protons and so on. The electrons get their mass from the interaction with the Higgs field. The protons get their mass from the field energy of the quarks and gluons. All right, so there's more about mass and force in section 4.1. Well, let's go on to section 4.2, which is called Newton's Laws of Motion. And I'll start with a little history, kind of a short history about the discovery of Newton's laws of motion. Isaac Newton lived 1642 to 1727, a little after Galileo. In fact, Galileo died in 1642, and Isaac Newton was born in 1642. And he lived a fairly long life. He lived until 1727. And he published the 3 laws of motion in a famous book, the Principia. It was all written in Latin, of course, in those days. That was published in the year 1687. Before that, before 1687, Newton was a somewhat obscure professor of mathematics at Cambridge University. After the publication of Principia, after 1687, he became the most famous scientist in the world. In fact, he's still today regarded as the greatest scientist in Western civilization. Newton solved the principal scientific problem of his time, which was, why do the planets revolve around the sun in the ways that are observed? Before Newton, people thought the sun revolved around the planets. Well, no. It was really Galileo and Kepler who determined that the sun doesn't revolve around the planets or around the Earth. All the planets, including the Earth, revolve around the sun. That was the Copernican theory, proven by Kepler and Galileo, who lived a bit before Newton. So the problem was to understand why. Why do the planets revolve around the sun in the ways that were observed by people like Galileo and Kepler? And Newton asked that question. And all the scientists of the day were trying to understand why the planets move in the ways that were observed. To solve the problem, Newton invented calculus. He invented the laws of motion, which we're studying in Chapter 4, and he invented the theory of gravity, which we'll come back to in Chapter 9. Newton wrote, toward the end of his life, he wrote, "If I have seen further than others, it is by standing on the shoulders of giants." And he must have been referring to Galileo and Kepler, because he was using their observations, and seeing further means understanding why those observations, what explains those observations. The 3 laws of motion, published by Isaac Newton in 1687. Over 300 years ago. And we still use the same laws of motion today. This is something that's really stood the test of time. Every mechanical engineer makes use of Newton's laws of motion to design motors, engines, any kind of mechanical system. NASA uses Newton's 3 laws of motion to calculate the motion of satellites or rockets. So what are the 3 laws of motion? The first law says, if the net force on an object is 0, then the object maintains constant velocity. This is sometimes called the law of inertia, It was described by Galileo and Kepler as an example of inertia. If something is moving, it'll keep on moving. Its motion won't change at all if there are no forces acting on it. An object at rest remains at rest. An object at motion remains in motion, and the velocity is constant if there's no net force acting on the object. This was a great discovery in the time of Kepler and Galileo. It contradicts the ancient theory of Aristotle. Galileo sort of overthrew the ancient theory of the Greek philosopher Aristotle. Aristotle said an object in motion will eventually come to rest. That contradicts the law of inertia, which says an object in motion will continue in motion with a constant velocity if the net force is zero. It's a very common misconception today to think like Aristotle. In order for something to move, something else must be pushing it. No, that's false. The best example of this is the Earth. We could either talk about the Earth revolving around the sun. What's pushing the Earth around the sun? Well, there's nothing pushing it around the sun. It's pulled toward the sun by gravity, but there's nothing pushing it so that it moves on an orbit around the sun. An even better example is rotation. Why does the Earth rotate? One rotation every 24 hours. In 24 hours, the Earth turns around one time. Why? Why doesn't it slow down? Why doesn't it slow down and stop? Aristotle would say, if something is rotating, there must be something pushing it to keep it moving. But no, there is nothing, there is no force which is causing the Earth to rotate. I guess since it's rotation, you'd call it a torque. Is there a torque that keeps the Earth moving? No. Why does the Earth rotate? Inertia. That's the first law. Then there's the second law. Now, the first law concerns the case where there's no force or there's no net force. The second law concerns the case where there is a force. When there's no force, the velocity is constant. But when there is a force, the velocity will change. And that's Newton's second law. But Newton's second law is more precise than that. An object's acceleration and the net force acting on it are directly proportional, and the constant of proportionality is the mass. So we can write this equation, F equals ma. Now you have to be careful. What's this F? This F means the net force. You could have an object, and we'll often see examples of that, where there are multiple forces acting on an object. So what controls its acceleration? It's the net force. It's the sum of all the multiple forces. And remember, force is a vector. So you can add two vectors and get zero. It's not like numbers. You can't really add two numbers and get zero. Well, yeah, you can. If you add 1 and -1, if you add those two numbers, you get 0. So if you add a positive number and a negative number, you may get 0. And forces have directions, so forces also. If you add two forces, or multiple forces, you might get 0. Then the acceleration would be 0. You'd be back to Newton's first law. But, if there's a net force, then there must be acceleration equal to the net force divided by the mass of the object. Now, mass is an intrinsic property of the object. Every object has a certain mass. And the acceleration is the force divided by the mass. So the larger the mass, the smaller the acceleration. So you see how mass is a measure of inertia, the resistance to change in velocity. Change in velocity is acceleration. The larger the mass is for a given force, the smaller the change of velocity. So mass is a measure of inertia. It's a measure of the resistance to the change in velocity. This will be the equation of most importance in Physics 231. In fact, this is the starting point for all of science and mechanical engineering. Modern science, we live in a scientific age following the scientific revolution of 300 or 400 years ago. It all starts with this equation relating force, mass, and acceleration. So we call this the equation of motion. Newton's second law. Now Newton's third law. Newton's third law is not so much about motion as it is about forces. It's a property of force. You can't have a force with only one object. You have to have two objects to have a force. You know, suppose you have nothing but one object. It can't exert a force on itself. So in order to have a force, you have to have two objects. You have to have one object which exerts the force, and you have to have another object which experiences the force. A force is a push or a pull. Consider a push. Well, there's one object pushing, and then there's the other object being pushed. There have to be two objects. The third law says when two objects, call them A and B, interact, there will be two forces, FAB and FBA. Those two forces are equal in magnitude, or strength, and opposite in direction. In other words, let FAB be the force that A exerts on B. So A is pushing B. There must be another force, FBA. That's the force that B exerts on A. B is pushing back. It must. And FBA is negative FAB. So the magnitudes of these two vectors, or the strengths of the forces, are equal. But their directions are opposite. So if FAB points in that direction, then FBA points in that direction. No, not in that direction. In that direction. Here's FAB, here's FBA. It's in the opposite direction. Has the same length. The vectors have the same length. That is, the strengths are equal. Now, this is the way that Newton expressed the third law. Everyone knows this sentence. Everybody, probably in the entire world, knows for every action, there's an equal but opposite reaction. That's the way Newton wrote the statement of the third law. Everybody knows that statement. Most people don't know what it means. Many people, and I would say, in fact, probably most people, do not comprehend Newton's third law. They've heard of it. They've heard that for every action there's an equal but opposite reaction, but they don't understand what it means. This is a subject of many misconceptions. Let me give you an example. So consider a collision between a small car and a big truck. It's pretty obvious that while they're colliding, they're both exerting forces on each other during the collision. Which force is stronger? If you picked a random person off the street and you said, suppose there's a collision between a small car and a big truck, which exerts a larger force? Most people will give you the wrong answer. Most people will believe the wrong answer. Study the examples in the book. Another good example is a tow truck. A tow truck, which is a big truck, is pulling a little car connected together by a chain. They start out at rest, then the tow truck accelerates forward, the car gets pulled along. The tow truck, let me put it a different color, the tow truck is pulling the car in this direction. So the car will accelerate in that direction because the acceleration is in the same direction as the force by Newton's second law. At the same time, the car is pulling the tow truck in this direction. Equal but opposite. The car is pulling on the truck just as hard as the truck is pulling on the car. Now, it looks like the net force would be zero, so they won't go either way. Why do they go in the direction of motion of the truck? Why don't they go in the direction of motion of the car? Well, these aren't the only forces acting. Remember, the truck and the car are in contact with the road. So there are other forces besides these two. There are forces of the contact between the tires and the road. There are frictional forces. The car is probably not in gear. The car has been shifted into neutral. The car is shifted into neutral, so these wheels will just rotate in response to the force. But the truck is not in neutral. The truck is engaged. And so as its engine turns the wheels, everything accelerates to the right. So these two forces are equal but opposite. But the forces down here of contact with the road there's a force here as the engine drives the wheels, there's a force that way. And the force here, well, let's suppose the car is shifted into neutral. Then there's really no force preventing the car from moving forward. So you see the net force on the truck, it'll have this small force pulled backwards, but it'll have this much stronger force pulling it forward. So the truck will accelerate forward. And as for the car, well, the only force acting on the car, if it's in neutral, will be the force of the chain pulling it forward. But here's Newton's third law. Newton's third law is right here. These two forces are equal but opposite. We'll eventually come to momentum, and Newton's third law has the implication that momentum is conserved. That'll be a later chapter. Here's an example problem. Two vehicles collide head-on. Let's suppose we have some object, let's call it a cart. Let's have a cart with a mass ma and a velocity va. And suppose we have another cart with a mass mb and a velocity v sub b. And they're going to collide. They're going to engage in a head-on collision. We can just think of this as an example of one-dimensional motion because they're both moving on the same line. They're both moving on this line. During the collision, each vehicle exerts a force on the other. The collision lasts 0.67 seconds. After the collisions, the two vehicles stick together. Then fill in the table. What's the force that A exerts on B? What's the force that B exerts on A? What's the acceleration of A? What's the acceleration of B? What's the final velocity of the two carts stuck together as they're moving after the collision. We have to know what the masses are. So let's say the masses are given as ma and mb. You have to know what the initial velocities are. So let's say the velocities before the collision are va and vb. vb is negative. So the initial speed is 6.2. The final speed is 5.5. The final velocity is minus 5.5. And after the collision, they have the same velocity because they're stuck together. Let's call that v sub f. And part of the problem is to calculate v sub f. Okay, so how are we going to solve this problem? Well, we have a bunch of equations. One thing we know is FAB is equal to negative FBA. That's Newton's third law. We also know FAB is MBAB, while FBA is MAMA. That's the two applications of Newton's second law. We also know the acceleration is the rate of change of velocity. So the acceleration of A is v final, that's its final velocity, minus VA over delta t. And in the same way, the acceleration of B is the rate of change of velocity. Its final velocity is also Vf, but its initial velocity is Vb, which is in fact negative. So AB is Vf minus Vb over delta t. Delta t is given. Delta t is this time when the forces are acting. So these two equations are just equations of kinematics we've studied before. So if you look, we have 1, 2, 3, 4, 5 equations, and there are 5 unknowns. 1, 2, 3, 4, 5. So you know from high school how to solve equations where you have multiple equations with multiple unknowns. That's what you have here, 5 equations with 5 unknowns. You just have to use algebra, so the rest is just algebra. Solving 5 equations with 5 unknowns. And of course the answer is FAB is equal to minus FBA. Well, that's Newton's third law. AA, well, MA is the massive object. MB is the less massive object. So AA will have a smaller acceleration because it has a larger mass. So the acceleration of A will be small because it has large mass, and mass is the resistance to change of velocity. AB will have a larger acceleration. And as for the final velocity, well, you know, if these are, just think of it in your mind's eye, these two will collide, stick together, and they'll be moving, probably, since this one's more massive, they'll probably be moving slowly to the right after the collision. I should put that on the homework. Okay, I'll try to make sure that's one of the homework problems. Now, the last section of Chapter 4 is Newton's laws and uniform circular motion. We recall from Chapter 3, we already know if an object moves on a circle, let's say at its constant speed, then the acceleration is directed towards the center of the circle. That's the centripetal acceleration, and we've studied that before. We know that its direction is towards the center, and we also know the magnitude of the acceleration. A is a vector. This A doesn't have an arrow over it, so it's not a vector. This is the magnitude of A. It's v squared over r. Now, if there's an acceleration, there has to be a force. According to Newton's second law, there must be a force acting on the object that's moving in the circle. And the force has to be equal to the mass times the acceleration. That's Newton's second law. If there's a force, if there's a net force, there must be an acceleration. If there's an acceleration, there must be a net force. Now, we understand the acceleration. It's v squared over r. But some other theory has to describe the force. So you have to identify, you know what the acceleration is. It's v squared over r. You know what v is. That's the speed. That's the circumference of the circle divided by the period of revolution. So we know what a is. Some other theory has to tell us what F is. So here are some examples. F could be gravity. For example, consider the moon revolving around the Earth. It's moving on a circular orbit. It has to be pulled towards the center of the circle. That's the centripetal force. It's the gravitational force of the Earth that's pulling it towards the center of the Earth. Or F could be string tension. That's an example in the book. Example 4-4.11. Or it could be friction. That's another example in the book. Think of a car traveling around think of a race car traveling around a circular track at 60 miles an hour. It's at every point it's accelerating towards the center of the track. It's not ever getting any closer to the center of the track. It's staying on the track. So it's accelerating towards the center, but it's not moving towards the center. Don't confuse velocity and acceleration or their directions. What's the force that's keeping the car on the track? It's the friction between the wheels of the car and the track. There's friction pulling the car towards the center of the track. Suppose you replace the track by ice. Well, then the race car wouldn't be able to move around the circle at 60 miles an hour. It would slide. It would slide on the ice. It would just slide off. No force, constant velocity. It would just slide off the track. That would be an example where the centripetal force is a force of friction. So read chapter 4 and read over these examples carefully. Now we can write an equation relating the force and the speed. Here's an example. Let's calculate the period of a low Earth satellite orbit. So I have a satellite orbiting the Earth not far from the surface. So it's a low Earth orbit. We call that a low Earth orbit because it's close to the Earth. It's like this. Here's the center of the Earth. That point is the center of the Earth. Here's the radius of the Earth. That distance is the radius of the Earth. Here's the height of the satellite. We could call that, we call that H. That's the height of the satellite above the surface of the Earth. Now let's see, I'll call this radius R. No, I had this right the first time. I'll call this radius R. That's the radius of the Earth. That's 6,371 kilometers. It's kind of an average measure of the radius of the Earth. 6,371 kilometers. The height is 29 kilometers. So the radius of the orbit, which I'll call little r, is 6,400 kilometers. Now what's the question? The question is, calculate the period of revolution. How long does it take the satellite to go around the Earth once? That's the period of revolution. Now it's moving with a constant speed. Well, Newton's law of gravity says the force is g times the mass of the Earth times the mass of the satellite divided by r squared, where r is the distance from the satellite to the center of the Earth. And Huygens' formula for acceleration is v squared over r. Force has to be the mass, we're talking about the mass of the satellite, times v squared over r. F equals ma. That's Newton's second law. So if I look at these two equations together, gmm over r squared is mv squared over r. The mass of the satellite cancels out. It doesn't depend on the mass of the satellite. I can solve for v, multiply both sides of the equation by r, take the square root. V is the square root of gm over r. So that's the speed of the satellite. Now the speed of the satellite is the circumference of the circle divided by the period. So the period is 2 pi r over v. The time is the distance over the speed. The time for one orbit is the distance of one orbit, one circumference, divided by the speed. And the speed is a square root of gm over r, so 1 over the speed is the square root of r over gm times r times 2 pi. So the period is 2 pi, the square root, r cubed over gm. Now, gm over r squared is the acceleration due to gravity at the surface of the Earth. That's 9.81 meters per second squared. All objects near the surface of the Earth, and because this is a low Earth orbit, I can say this is near the surface of the Earth. All objects near the surface of the Earth have the same acceleration due to gravity. Discovered by Galileo, explained by Newton. Newton showed that's gm over r squared from the theory of gravity. And Galileo showed that's a constant, and you can measure that constant at 9.81 meters per second squared. So I'm going to calculate the period. It's 2 pi square root of r cubed over gr squared. Plug in the numbers. This will be in standard units, so the answer will come out in seconds. It'll be some number of seconds. That will be a homework problem sometime. So now you got to calculate the numbers. I don't remember the exact number, but it's about 90 minutes. That satellite goes all the way around the Earth and comes back to the same point in about an hour and a half. All right, so that completes the video for Chapter 4. This will be on the YouTube channel, and its name will be Introduction to Chapter 4. So now that you've had an introduction to Chapter 4, read Chapter 4. Read it carefully, read it and study it. Spend several hours reading a chapter, take notes. Open up your physics notebook, take a page of notes of the important equations that you find in Chapter 4. And then you'll be ready to do the homework problems.